Welcome back, everybody. Today's lesson, talking about different sets of numbers and the idea of closure in closed sets of numbers. Let's first start off with the definition of what a closed set is. A set of numbers is a closed set under an operation if the result of the operation on any two numbers is in the set that is also a member of that set. So, talking about the four operations, either addition, subtraction, multiplication, or division, and also talking about different sets of numbers: rationals, irrationals, whole numbers, integers, real numbers. We got to think about what those sets of numbers are. Basically what it says is that, okay, if you have a number, so let's focus on addition for a minute. So like, say a set of numbers, integers, an integer plus another integer equals another integer. If that is always going to be true for any integers we talk about, then we say the set is closed. If it's not, we just say not closed or open. Here's some quick examples just kind of illustrating that. It says integers are closed under addition, like I just said, because the sum of any two integers is always another integer. So for instance, 2 plus 3 equals 5. 2 is an integer, 3 is an integer, 5 is an integer. Negative 7 plus 3 equals negative 4. Negative 7 is an integer. Positive 3 is an integer. Negative 4 is an integer. It turns out this is going to be true for any two integers you can think of. If you take an integer plus an integer, you'll always get a third integer. However, you can't say that for division. Integers are not closed under division because the quotient of two integers is not always another integer. For example, 1 divided by 2 is 5. 1's an integer, 2's an integer, but 0.5 is not an integer. 0.5 is a fraction, could be written as 1 over 2. So this, you just need one example to disprove it, and then you would say not closed rather than closed. Let's look at another example here. Whole numbers. Whole numbers are not closed under subtraction because the difference of two whole numbers is not always another whole number. For example, 2 minus 6 is negative 4. Whole numbers, remember, are starting with 0 and going 1, 2, 3, 4. Whole numbers are positive whole numbers, including 0. 2 is a whole number. 6 is a whole number. However, if I subtract them, I get negative 4. Negative 4 is not considered a whole number. So that's kind of illustrating the differences. Now we're going to talk about some different problems here, and we'll discuss them as we go here, kind of illustrating this concept of closed set and not closed set. All right, we're going to complete the statements here with either the word closed or not closed, and I will just use an NC for not closed. And let's just use a C for closed. Real numbers are blank under addition. So it turns out real numbers are closed under addition. You can take any number you can think of, any real number, not imaginaries, but real numbers. If you add one real number to another real number, you will always get another real number. Integers, however, not closed, NC, not closed under division. All right, and that's because, here's an example that proves that. 3 over 4, 3 divided by 4. If I take 3 divided by 4, let me write it like this. 3 is an integer, 4 is an integer. However, I could express it like 3 over 4, which is a rational number, or the decimal 0.75. Both of those are rationals, not integers. That's why we say not closed. Irrational numbers are not closed under multiplication. Here's an example of that. The square root of 2 times the square root of 18. Now if you notice, square root of 2 and square root of 18 are irrational, but multiplying those yields the square root of 36, and that is something we can actually find. We can find the square root of 36 giving us 6. 6 is rational, not irrational. That's why we say not closed. And then lastly, rational numbers are blank under subtraction. Rational numbers are closed. You can take any number that can be written as a fraction, like 1/2, and let's subtract from it 1/4. 1/2 minus 1/4, 1/4. Yeah, rational number minus a rational number will always equal another rational number. Positives, negatives, if it can be written as a fraction, a rational minus a rational will always equal a rational. Let's look at this one here where we are saying which equations support the fact that rational numbers are closed under addition. All right, the key here on this one is just focusing on the word rational. Look at our choices here. We'll go through and simplify them and actually figure out A is a true statement. 3 square root of 5 plus square root of 5 equals 4 square root of 5. However, that does not support the fact that rational numbers are closed under addition. The fact that square root of 5 here, we're talking about square root of 5, that's an irrational number. That's not going to work. And B, even though B is a true statement, look at square root of 10. Square root of 10 is irrational. It's not going to work here. Now let's move on to C. We got a rational number. We got a rational number. And this is also rational. We can write 1 as 1 over 1. So this works. C is a true statement. C does support the fact that rational numbers are closed under addition. Don't be fooled on D. Square root of 16, square root of 16, square root of 16. Anytime I see square root of 16, I could actually write 4. And then that gives us 12 plus 12 equals 24. True statement. All of those numbers can be written as fractions. 12 over 1, 12 over 1, 24 over 1. True statement for D. All right, looking at another one here. What number can you multiply by negative square root of 2 to get a rational number? So that's what we're going to do. We're going to multiply each of those by negative square root of 2. Notice the negative is on the outside, and that means if it was on the inside, it'd be an imaginary number, which we're not talking about here. Probably won't talk about imaginary numbers until you get to your Algebra 2 class, but they do exist. So I'm multiplying each of these by square root of 2. A, I get 0. 0 can be written as a rational number, like 0 over 2, so A works. 2 times square root of 2, that does not work. That's an irrational number. Square root of 2 times square root of 2 is a square root of 4, and that negative sign's still out in front. This simplifies to negative 2, which can be written as 2 over 1. C works, and then D does not work. That is an irrational number. So the right answers here, A and C. Next one here, which expressions simplify to a rational answer? Let's just go through and simplify and see. Square root of 5 times square root of 5 is 25. That can be written as 5. 7 square root of 3 times 3 square root of, times square root of 3 is 7 times square root of 9. Square root of 9 is 3. This is 7 times 3, which is 21. Can be written as a rational, just like 5 can. 2 square root of 9 times square root of 4 can be simplified to 2 square root of 36. 2 times 6, 12. 12 can be written 12 over 1. So far, A, B, and C. Let's see if all three of them do. Square root of 3 times square root of 16 is square root of 48. If you put that in the calculator, you get that non-repeating decimal that goes on forever. So D is irrational. A, B, and C, though, simplify to rational answers. All right, so here's a proof statement, and we're going to prove by what's called a contradiction. And you do a lot of proofs in geometry, but you can apply the concept of proof to an algebra topic as well. So we're going to complete the blanks here with the word rational or irrational. It says to prove that 3 square root of 5 is irrational, let's assume the product is rational and set it equal to A over B. Okay, so we're kind of doing an assumption here. We're going to say 3 square root of 5, and we're going to set it equal to A over B. A over B being a rational number where B can't be 0, otherwise it doesn't work. Isolating the radical gives us A equals 3 over B. So what happened here algebraically is I divided by 3, and we know that dividing by 3 is like multiplying by 1/3. That's why we can write it like this, A over 3B. The right side of the equation is blank. Now the right side here, A over 3B, is rational. I'm writing that expression, A over 3B, can be written as a fraction. It is a fraction, in fact. So we're going to put rational here. However, as we finish on, because the left side of the equation is irrational, Notice the square root of 5. That is an irrational side. This is a contradiction, and that's true. You can't have a square root of a number, an irrational, and set it equal to a rational quantity. All right, because of this contradiction, because these two just can't be equal, the assumption is wrong, and therefore this quantity 3 square root of 5 is irrational. So this was kind of a, a word out where we're writing out the reasoning and the we're thinking through how can we prove that a number is irrational. So this is just a quick little contradiction type proof. All right, thank you for watching. I hope you understand the concept of this closure and closed sets of numbers a little bit better.